Okay, good evening, everyone. I am Priya, one of the organizing co-chairs, and I welcome you all to the second day of week 7 of IEEE Symposium on Data Analytics and Internet of Things. IEEE Victorian section presents this symposium in collaboration with Computational Intelligence Society, IoT Community, and University of Melbourne Student Branch. Just to quickly run you through the schedule of the symposium, it's going to run for one more week until 19th of November, with events happening only on Tuesdays, Wednesdays, and Thursdays, either as afternoon or evening sessions. Like next week, we have one afternoon session as well on the Tuesday. Since you have registered for this week, you will be on our emailing list and will receive emails about the event schedule for the following week as well. You can follow our website and social media pages for more updates. So today's topic is applications and advancement in satellite technology and agriculture. The talk will be for around 45 minutes with last 15 minutes dedicated for question and answer session. Please use the question answer tab at the bottom of the window to post your questions. So we have Les Davey as a speaker for this event. Les is the managing director of Omnispace LLC in Australia. He graduated in electronic engineering from Swinburne University of Technology in 1971. Les has 45 years experience in telecommunications industry with 22 years with Telstra. He has a wide range of experience in both government and private industry. He has worked for the last 20 years in the satellite industry on engineering, regulatory operations, and business development projects. He has published a large number of technical papers on satellite broadcasting and radio communications, and has presented many papers at major domestic and international conferences, and is a long-time IEEE member. Thank you, Les, for joining us today. The floor is all yours.
Yeah, thanks, Priya, and good evening, everyone. In the IoT seminar presentation so far, we've been provided with a great overview of IoT and its applications. My presentation tonight is going to be a case study of how satellite is being used for an agricultural technology trial in rural Victoria. This trial is a joint project with US satellite company Omnispace and Melbourne Polytechnic. They have a Vineyard operation at Areadale. So far there's been a lot of hype about terrestrial 5G and its use for IoT, but really it's only satellite that can provide essential Australia-wide coverage, especially in rural and remote areas. So the motivation for this trial, firstly to establish an agricultural technology satellite IoT trial to demonstrate this capability to clients. Next, to test commercial agricultural technology sensors and the associated software. And finally, to use the data that's been collected so far to improve Vineyard operations. So the focus of this presentation is going to be on the transport and the sensor elements of the IoT trial, with some observations on the agricultural aspects. So the topics I'm going to cover is just briefly a review of what an IoT system is. We should all know that by now. The particular trial objectives, the elements that make up a satellite IoT trial. Then just a bit of information on the Melbourne Polytechnic Areadale Vineyard and the sensor equipment that is being used there. Next, just a brief description of Omnispace and the non-geostationary spacecraft and associated ground equipment that's being used for this trial. Next, a description of what the Vineyard application software can do that processes the data, and some example results that have been obtained, and finally summarising what we've learned from this trial. So this slide just indicates the main elements of an IoT system, starting with the hardware. We have sensors that collect the data. Then importantly, we have a transport system that transports the data ultimately to the internet. And in this particular trial, that transport mechanism is via satellite. And then finally, analytic software that makes use of the data that's been collected. So looking at the particular features of satellite and how it can be used for IoT, principally the benefit of satellite is that it can provide large area coverage, Australia-wide coverage, as I mentioned, and that particularly means coverage to urban, rural and remote areas that either don't have terrestrial coverage or it's very expensive. The other thing is with the spacecraft already being in orbit, it's quite quick to establish a ground system user terminal, and that it's relatively affordable and the ongoing operational cost also. Another particular benefit of satellite is that it is pretty reliable if you compare it with terrestrial cellular mobile systems that can be impacted by floods and bushfires that we know all about in Australia. And just a technicality for IoT satellite applications, we talk about MSS, mobile satellite service, which you'll see a bit later is distinct from the fixed satellite service. So what I'm going to do now is just talk briefly about the different types of satellites and the associated orbits that are used in satellite communication. Starting with the geostationary orbit satellites, these are very large spacecraft and they generally have a large bandwidth because of the frequency bands they operate in. They operate in an equatorial orbit at an altitude of around 37,500 kilometres above the Earth. But because of their equatorial orbit, they generally have poor coverage to the high, that should be latitudes at both the north and the south hemisphere. So good coverage around the equator, but poor coverage towards the two poles. The next type is medium Earth orbit. These are medium to large spacecraft, and similarly they have generally a large bandwidth. So they use a non-geostationary orbit, typically an altitude of around 10,000 kilometres. This gives them good global coverage, and in particular, good coverage at the high latitudes towards the poles. And the next type has become very popular. It's the low Earth orbit, which typically consists of large constellations of small spacecraft with smaller bandwidth. Again, non-geostationary orbits, typically altitudes that range from about 500 kilometres up to 1,500 kilometres. And because of the large number of satellites whizzing around, that have good global coverage also. Now just to talk briefly about the associated frequency bands. With the geostationary satellites, they operate in typically the C, the KU and the KA bands, and are moving to the higher millimetre bands. So on that slide there, you can see C band is 4 and 6 gigahertz, KU 12 and 14, KA 18 and 28 or 30 gigahertz, but we're moving to 40 gigahertz and above. So at those higher frequency bands, we have bandwidths up to around 2.5 gigahertz. For the MEO satellites, they operate at the S band, around 2 gigahertz, and also at the same bands as the geostationary satellite orbits. And regarding the 2 gigahertz, ACMA is currently replanning the 2 gigahertz band, particularly for the mobile satellite service and also for IoT applications. And then we come to the LEOs, and they the most popular bands are also the KU and the KA bands, but also some operate in the UHF band from 140 to 450 megahertz, the L band around 1500 megahertz, and the S band at 2 gigahertz. So these, because of these bands, often have smaller bandwidth, but the larger constellations are also using the higher KU and KA bands. This research only recently became available. The source is a New Skies research report on machine-to-machine and IoT via satellite, and in particular small satellites, and that came out just last month. And the revenue projections there are US dollars 600 million by 2029. And the breakdown by industry, you'll see that agriculture is quite a large expected application for revenue, 37%. Then maritime, ships at sea, 18%. Transport and cargo, logistics, 17%. So with other applications making up the remainder of the 28%. But certainly agriculture, particularly for the small satellite market, is seen as a big application. So just going over the IoT trial objectives, it's to use a non-geostationary satellite IoT system on an agricultural technology project. We needed to obtain an ACMA, the frequency regulator, a license for them at S-band. Up until recently, this particular band has been embargoed. Next, it was to investigate commercially available sensors and the associated gateway equipment, and to investigate the commercial Vineyard management application software to process the data, and also to establish a trial site that we could demonstrate to clients interested in satellite ag tech. So what I'm going to talk about now is the elements that make up a satellite trial, starting with the Vineyard and the sensor equipment. Then I'll talk about the satellite ground system user terminal equipment, a little bit on the spacecraft, the satellite Earth Station feeder link, which communicates with the satellite, brings the data back from the remote site and connects it to the internet, and also the data analysis software. So this is the end-to-end architecture of this particular satellite trial. Starting on the left-hand side, we've got two separate sensor nodes, which have sensor equipment in two different rows in the Vineyard. Those sensors communicate via an XB 915 megahertz link to the gateway equipment, located about 1 kilometre away from the sensor nodes. That gateway equipment via a satellite modem connects to the satellite. In this case, the satellite makes a pass every 6 hours. So when the satellite's visible, the satellite modem equipment connects with the satellite, sends the data up, and then the data is brought down at the Omnispace satellite gateway, which is at a place called Ningi in Queensland, about 45 kilometres north of Brisbane. And that's where it's put onto the internet. And finally, the data is available via the internet to run the application software. So now I'm going to talk about the Areadale Vineyard and the sensor equipment. So the Melbourne Polytechnic Areadale Vineyard, it's located in Ararat. If anyone knows Ararat, it's actually adjacent to the former Ararat Mental Hospital. The area that's under grape cultivation is 27 hectares, which is something like 68 acres, if people think in acres. Different areas throughout Australia are classified in different wine climate areas, and in Ararat it's a continental climate with a mean January temperature of 20.6 degrees, but February it can get very hot and dry, up to 40 degrees. The grape varieties that are being grown there are Shiraz, Sauvignon Blanc, Riesling, Cabernet Sauvignon, and Sangiovese, with a trend to the Italian varieties as we're seeing the effects of global warming. There's quite a large winery on the site. It's got the capability of processing 300 tonnes of grapes. It's currently processing about half of that. So in addition to the grapes that are grown in the vineyard, the other smaller producers bring their grapes in for processing at the winery. The trial was started on the 1st of February 2019 and will run it through till late February, perhaps later next year. So that means the trial have been going on. We'll have data from 2 consecutive vintages. That's an aerial shot of the vineyard. The area there in green is where the grapes are actually grown, and that highlighted point there sort of points in the general area of where the winery is. Now the sensors, and there's 2 separate nodes. Each of those nodes has a sensor for the air temperature, air humidity, air pressure, soil humidity, soil moisture at a depth of 300 millimetres and also at a depth of 600 millimetres. There's also a sensor for leaf wetness, one for wind speed and direction, and also for the battery level, which is flow charged by a solar panel that you'll see a bit later. So this is what the sensor node looks like. You can see the wind direction, wind speed equipment at the top. To the left of the solar panel is a tipping bucket rain gauge. And then the sensor electronics are mounted underneath the solar panel, and the 2 cables that are going down go down to the soil moisture sensors. And also, although you can't see it there, there's an antenna with a Zigbee connection back to the gateway. And this is what the gateway equipment looks like. It's mounted on the vineyard pump shed, and it has several antennas. There's 3 monopole antennas there, one at 900 megahertz for the Zigbee communication with the nodes. It's got a backup 3G, 4G mobile service. Ararat has a good cellular mobile service, and there's also a 2 and 2.4 gigahertz Wi-Fi monopole. Now to look at the satellite ground system user terminal. You can see it there mounted on that pole, which is also attached to the pump shed. So you can see it's a relatively small box of RF electronics that transmits and receives from the satellite at 2 gigahertz. And on top, you might be able to make out an omnidirectional antenna. this just provides a bit of information on the RF terminal itself, gives you an indication of the size, around 300 millimetres wide by about 450 millimetres long. So if anyone's got any questions, we can come back to that later. Now to look at the spacecraft itself, that's what it looks like. This is the Omnispace F2 satellite. It was built by Boeing as part of a family of Boeing satellites. It's reasonably old these days, and this provides some information. The top part, information on the orbit. You can see there the perigee and apogee are the height above the Earth, so around about 10,500 kilometres. It's in an inclined orbit of nearly 45 degrees, which means it has a period of about 360 minutes or 6 hours. It was launched a fair time ago, June 19th, 2001, but it's still travelling well. That's just a picture that shows the solar cells, which are sort of, folded out after launch. And it actually was quite advanced with the receive and transmit antenna arrays that were used at that time. It's quite common now. That's the sort of pattern, cellular pattern that the satellite can project onto the ground. So you can see it can cover quite a large area. There are 163 spot beams. So, if I had a picture that showed that over Australia, you could see it provided coverage to all of Australia. That shows a typical pass of how the satellite would travel, starting or approaching from the bottom left-hand side, crossing Australia and then heading off to the higher latitudes. This is a picture of the satellite Earth station, which Omnispace has at a place called Ningi in Queensland. And on this site, we have 5 quite large 7.6 metre diameter fully tracking antennas. They're both fitted with S-band and X-band feed horns, so they can communicate in those 2 bands. It's actually on the site of a Telstra exchange and an NBN Co exchange, so it now has excellent high-speed interconnection to the internet, and we have a UPS to provide backup in case the primary AC power supply goes down. Now to talk about the application software. So as I mentioned, the sensor data is accessed online via the website. Each of the sensor parameters can be plotted over a selectable time period, which I'll show you soon. Importantly, the software with its weather information can predict the likelihood, in particular, of frosts. Frosts late in the growing season when the berries are just formed, typically October, November, can do a lot of damage. So having early warning of that, appropriate action can be taken. Another important aspect of the application software is for water management. Ararat's a fairly dry area, so if you can have the data on what the soil moisture is at the particular depths, then you can control your irrigation and not waste water unnecessarily. Another important issue in vineyard management is the need for pesticide spraying, both to control insects and also under certain weather conditions when you can get fungus. So the software has the capability to give warnings of the need for pesticide and fungus spraying. It also has the capability for a diary facility, which allows you to schedule these forthcoming events and also to record particular events. So this is an example plot. The horizontal scale there is time at 6-hourly intervals, which corresponds to each of the satellite passes. And you can see the air temperature variation there. And towards the middle, you can see the temperature is getting down to 0 degrees. And this is in July. Later on, it can get down to about 5 degrees there with quite severe frosts. This is a plot of air pressure. This is often an indication of storm and weather patterns. You can predict what action you might need to take. Rainfall gives an indication of the rainfall during July. Again, coming in bursts. But if we looked, in the January and February, months there would be very little or any rain. An interesting sensor is one that monitors leaf wetness. So in addition to the amount of rain, this sensor gives an indication of how wet the vines might be. And if there's no winds to dry the leaves out, this can often lead to fungus conditions. This is an indication of the soil moisture at a depth of 300 millimetres. The vertical axis is centibar, which is pressure. So the calibration for soil moisture that vineyard operators and probably also farmers understand is what that moisture corresponds to in centibars. This is the display for the same period at another 300 millimetre down depth at 600 millimetres. So this is a slide that's really been prepared by the winemaker there, which happens to be my son Andrew. And after the first vintage, this is really what he considered were the benefits of this trial. So the water management in particular, he found to be very useful, but it did mean that we had to do a bit of experimentation with the rainfall and the soil moisture sensor to calibrate them properly to make sure that the results we were getting were quite, we could believe in. The software was developed in Europe, and we found that the rainfall in particular, the calibration wasn't consistent with Australian rainfall. As I mentioned, the frost warning capability proved to be very useful. The late frosts, typically around November, can reduce the grape yields at this vineyard by about 20%. Also, the pest control was found to be very useful for the timing and the quantities of the pesticides and fungicides that were sprayed. In terms of the ease of use, as typical with software, there was a learning curve for both the sensor installation and the setup, but in particular for the calibration. Also, we had one weather station that failed, and we haven't replaced that. But overall, once we got familiar with the application software, it was considered to perform quite well. So this is a summary, and I see I've got sped through this fairly quickly. So at the end, please ask me some questions. So we have conducted a satellite IoT agricultural tech trial at this vineyard. It's been going, as I mentioned, now for one complete vintage, and we're now in that second vintage. Good experience has been gained with commercially available ag tech sensors and the associated analysis software. But we've learnt particularly that the calibration and reliability of the sensor data is important to have confidence in the results. If you haven't got data that you can believe in, well, then it's obviously not very useful. Another thing I think is a useful tip is that we purchased this trial equipment, both the hardware and the software, as an integrated system, and that made the task of installing it and getting it operational a lot easier. So particularly, for people like farmers that, might not be tech savvy, I would certainly recommend that if they want to set up an IoT system for their farms, then I would recommend that they buy a complete integrated hardware and software system that they can have confidence will give them good data. And finally, the satellite IoT system that we've trialled can obviously be applied to other agricultural applications, and also other applications that we mentioned during the discussion on the revenue. If people want to look at it a bit more detail, they're the two references that I can pass on to you. And Priya, back to you. I've raced through it.
Thank you, Les. Thank you for the great talk. No, you didn't race. It was good. It was very informative, and I'm sure everyone found it interesting too. Now we open the floor to questions. Do we have any questions for Les? You can also raise your hand, and I will unmute you. So if you want to talk directly, you can do that too.
Les, I have a question. Thank you for your talk. I just wanted to know, maybe I missed it during your presentation, but I wanted to know from how do you send the data from the sensors to the satellite internet? I mean, so every bit of information that sensors generate, it goes through the satellite internet, or no? You filter some of the data in the gateway. Can you explain about it?
Yes. What happens is that the gateway equipment, which is connected to the sensor nodes via an XB wireless connection, every 15 minutes, it will send a command to each of the two nodes and say, send me the data you have from each of those sensors, and then that is accumulated at that gateway. And then when the satellite, in this case, passes every 6 hours, that collected information connects to a satellite RF modem via an Ethernet connection. So the gateway equipment you saw on the side of the pump shed is connected to that pole-mounted RF modem via an Ethernet connection. Then the satellite modem communicates directly with the satellite as it's passing. Typically, the satellite will be in view for about 10 to 15 minutes. Then that information is then stored on the satellite, and as you saw, the satellite then moves towards the north, and when it becomes in view of the satellite Earth station at Ningi near Brisbane, then that large satellite antenna, 7.5 metre antenna, is tracking the satellite when it comes over the horizon. And again, when it is in view for about 10 or 15 minutes, it communicates with the satellite, takes down all the data that's been collected in that last 6-hour period, and then on the ground connects that to the via the internet and makes it available for analysis by the application software.
Okay, thank you. That's great. And just a follow-up question. Is there any limitation about like the amount of data that you can send to the satellite every time? Or, I mean,
yes, that's determined by the data, the modem itself. Typically, for that uplinking, it's about 150 kilobits per second. So that is sort of relatively slow, but the downlink goes up at 2 gigahertz. Sorry, the uplink goes up at 2 gigahertz, and then the communication down to the Earth station is at 8 gigahertz, larger bandwidth, and it can take down megabytes of data in that 10, 15 minute duration that the satellite's in view.
Yep, thank you. Thanks for explaining that.
Thank you, Les. We have a question. Can you also throw some light on IoT sensors for precision farming and agriculture?
I'm not familiar with precision farming, but there are a huge number of sensors available. Could the question be a little bit more specific? Unfortunately, I don't know anything about precision farming, which I think means, levelling the fields and making sure that the rain is used effectively. But could the questioner give me some more information?
Would it be possible to give a little bit more information on precision farming?
Hi, Liz. I was more intending towards how the data processing and analytics is being done. Basically, like monitoring the livestock or vehicle monitoring using the IoT sensors. On that.
Yes. What we did was buy a commercial package that was initially developed for Vineyard applications in Europe, and has been adapted to our application here in Australia. One of the issues was that because we're using a non-geostationary satellite that's not visible all the time, that was something that had to be adapted in the commercial software. So as I mentioned, I really would recommend that you look at buying an integrated package of both the software, both the sensors and the corresponding software. You can get into a lot of trouble if you buy sensors from, say, one vendor, and you then have to interface that to some gateway equipment, which could be from another vendor. And then you have to then get your data back somehow to the internet, maybe via satellite, and then to run application software that can work on that data. It's very risky to try and plug and play systems.
Yeah, thanks, Les. Thanks for that. Just a follow-up question on that. So when we say that we are connecting the satellites in the same thing for the sensors of agricultural sensors or maybe any other sensors, I assume the sensor processing with these satellites would be very simple on board. Like, what are the common onboard data processing steps within the satellite that you think are very existing or easy to implement?
Yeah, there's no actual data processing on the satellite. The satellite is just collected, buffered, and is passed down to the ground station. All the analysis is done via the internet with the application software.
All right. So if we take a drone in place for something like this, do you think that it would be similar in action?
Well, you've got the problem, I think, with drones of
Okay.
just battery life. So you're going to be using a lot of your battery power to keep it flying, and then you have to, have electronics that can capture and store the data.
Yeah. All right. Thank you so much. That was a nice talk. Thank you.
Thank you, Les. We have the next question from N. In principle, would it be feasible to use the same setup to go in the reverse direction and issue commands to sensors at the Vineyard?
Yes, that's a good point, N. That can certainly be done in principle. For example, you could want to turn, when you have a frost warning, you might want to start up the pumps that can water the vineyard. That's a way of raising the ground temperature to avoid the frosts. So in principle, that can be done, but for this particular trial, we didn't implement that. It's just taking the data from the vineyard and transporting it to the internet.
Yep, thank you. N, is that okay? Or do you have a follow-up question? Okay, thank you. I just have a quick question. So we talk about 5G technology and how it's going to support the realization of IoT with respect to smart cities and smart environments and everything else. So I just read somewhere that within the 5G framework, the terrestrial services can be augmented with recent development on high throughput satellite systems and other satellite constellations. So what do you think about 5G technology? How can it be integrated with IoT? Can it be done with aerial components? You said that it can't be done with drones, which and I agree to that. Can it be done with satellites for agriculture scenario or rural scenarios?
Yeah, yes. I think the last World Radio Conference established that, particularly in the 2 gigahertz S-band, that a hybrid network, so terrestrial with or satellite coverage with an auxiliary terrestrial coverage, that can be a good combination, and that's the frequency band that ACMA is making available through its replanning of the 2 gigahertz band. So that's the band that a lot of smaller IoT satellite operators want to use to provide a Australia-wide IoT service using both terrestrial infrastructure where it's available, and then out of terrestrial coverage, the satellite takes over. So I think that system is incorporated now in one of the, N would know this, but one of the 3G PP, I think it's called, or maybe you know, Priya?
No, I don't know. But that's good to know. Thank you. So Bala says hi. And Bala, do you have any questions for Les?
Yeah. Hi, Bala. I hope you're well. Bala was very keen to start up an IoT chapter under the Victorian IoT. So unfortunately, he got unwell, and they'd be very pleased that this seminar is taking place.
Oh yes, I think Bala is very happy with this symposium. That's what I understand from his emails, and we are very grateful to that he's been attending a lot of our talks. Bala, would you like to talk? Yes, he says he's happy. Thank you.
Okay, good to know.
Thank you. Do we have any other questions for Les? No. So I think we are good to wind up the session now. So thank you everyone for attending the talk, and a big thanks to Les for taking out time to share his knowledge on satellite technology. For tomorrow, we have Alan Harvey speaking on applications and advancement in energy harvesting for IoT systems at 5 p.m. So I look forward to seeing you all tomorrow and in the upcoming events of the symposium. Take care and stay safe.
Thanks, Priya.
Thank you. Thank you, Les.